Alright, hello students. This video is going over your Intermolecular Forces homework assignment. Again, like most assignments, you're doing this in your notebook. You don't have this handout, but I'm going to fill this out so you can follow along with the different problems I'm going to do. I'm going to go over 3 examples from this homework assignment. I'm going to do A, C, and D. And there are very specific instructions for how you answer the questions in this assignment. So I'm going to walk you through those steps. Question number 1 on this assignment is a different type of question. You should be able to answer that. I'm actually going to kind of cover it, but I won't explicitly do that question. But if we look at 2A, we're also going to use this flow chart, which you have in your notes. To answer these questions, it'll be really helpful to figure out which intermolecular force is the strongest in each of these, for each of these samples. So for 2A, we're going to follow the steps for answering this question. I'm going to go fairly quickly over the Lewis structures just because hopefully at this point you feel pretty good and solid with Lewis structures. If you have questions on that, you can watch the Lewis structures video. But the first step is to draw 2 Lewis structures for each of these compounds, and then a dotted line to represent the intermolecular force of attraction between them. And for each of these, so for A, you have 2 different compounds, and you have to draw 2 Lewis structures for both of them. Okay, so I'm going to go through, again, kind of quickly drawing the Lewis structure. The way that this compound is written out is giving you huge hints as to how it is connected. So these 3 hydrogens go with this carbon, these 2 hydrogens go with that carbon, and then that hydrogen goes with the oxygen. So I'm going to draw that Lewis structure. So there's that carbon. Then we have another carbon here which has 2 hydrogens, and then the oxygen which is bonded to a hydrogen. And this oxygen needs 2 pairs of electrons to complete its octet. Okay, but we need to draw 2 Lewis structures because really what we're doing is we're identifying the intermolecular force, the force of attraction that is between these molecules. So here's one molecule. And then I'm just going to copy and paste this exact Lewis structure. Draw another copy of it just below. In your notebook, if you want to do these side by side, that's fine. All right, so here's just another molecule of the same compound. But what we need to do is draw some dotted lines to represent the intermolecular force, which is the force of attraction that is between these 2 molecules. Okay, so just to reinforce this point, here is a model of that molecule. Okay, so the bonds that hold these atoms together in the molecule are covalent bonds, right? It's a sharing of electrons. The intermolecular force is the force of attraction that attracts another of the same molecule to each other. So the intermolecular force is between these 2 molecules. The covalent bonding are the actual sticks holding these atoms together in the model, right? It's the sharing of electrons. The intermolecular force is the force that is holding the 2 molecules together. It's an attraction, okay? So it can be a weak attraction, and they're far away, or it can be a pretty strong attraction. So our goal here is to figure out what the attraction is. And once we have our Lewis structure, we can use the flow chart to figure out what the intermolecular force is. To do that, we first need to ask, is the molecule polar or nonpolar? So if we look at this, remember polarity is all about symmetry. So is this molecule the same on all sides? Hopefully you said no, because this side looks very different. It has this oxygen over here. That's not on this side. It's it's not balanced, and so that means that it's polar. So that brings us to this side of the flowchart. Okay, the next question, if it's polar, we ask, are there any FH, OH, or NH bonds? In other words, in class we ask, is F on the phone, or is H on the phone? okay, is hydrogen on the phone. If hydrogen is bonded to any of these three elements, they're very electronegative. They're able to pull the electrons very close to it, exposing hydrogen. If H is on the phone, we would get hydrogen bonding. If H is not on the phone, we would get dipole-dipole forces. So let's check our molecule. Here is, we have a lot of H's. This H in particular is on the phone. It is bonded to oxygen. So since we have an OH bond, H is on the phone, so we would say yes, which means this molecule has hydrogen bonding. Okay, so the force that's attracting this molecule to another molecule of itself is hydrogen bonding. Okay, it's the intermolecular force. This is not a hydrogen bond. This is a covalent bond. The hydrogen bond is the attraction, the intermolecular force from one molecule to another molecule. Okay, so let's do the same thing. We're not done with this problem at all. We've just labeled the intermolecular force, but we need to draw two Lewis structures for the other one too. So again, I'm going to draw the Lewis structure. It is also telling us how it's bonded here. So these three hydrogens are bonded to this carbon here, which is bonded to another carbon. And then it says the oxygen has a double bond. So that means this carbon is double bonded to that oxygen. And then there's a hydrogen there. Right, so again, going kind of quickly through the Lewis structures. And then I'm going to draw another copy of it here. So some of these questions will take some time just because you have to draw the two Lewis structures, follow all your steps, draw some dotted lines here. Now we need to figure out what is the intermolecular force between molecules of this. Okay, so we'll use our flowchart. First question, is the molecule polar or nonpolar? Again, symmetry. This molecule is not symmetrical, not balanced, right? This side is very different from this side. So again, we have a polar molecule, so that brings us to this side. So we have to ask, is H on the phone? Do we have any FH, OH, or NH bonds here? So we have a lot of hydrogens, but none of them are on the phone. They're all bonded to carbon. So we don't have any of these bonds, so no. And that means we have dipole-dipole forces. Okay, so now we've done step 1, we've done step 2, we've labeled the intermolecular force for both of these. Now that we have both the forces, we need to compare them, and we need to circle the one that would have the higher boiling point. So what we're doing when we boil something is we're breaking the intermolecular forces. We're breaking the attraction between the molecules if we boil something. So we're not breaking the covalent bonds. Those are too strong. We're breaking this attraction here. So if we want one that has a higher boiling point, we want the intermolecular force that's the strongest, that's the hardest to break. So again, if you look at your flowchart, it tells you how to figure that out. These three forces, dispersion, dipole-dipole, hydrogen, they increase as you go this way. So hydrogen bonding is the strongest intermolecular force, and dispersion forces are the weakest. So if something has hydrogen bonding, it'll have a higher boiling point because it's harder to break those intermolecular forces. So since we have hydrogen bonding here, hydrogen bonding is stronger than dipole-dipole. So this one has the higher melting point. Or sorry, boiling point. Okay, you can just circle the formula for the one that has the higher one. All right, so that's the first example. Why don't we quickly go through these other examples here. 2C is between argon and krypton. So this is really easy for you to do Lewis structures for this one, but again, we need to follow our steps. So to draw Lewis structures for argon, it's just an atom of argon. So it's just going to be argon, and then you draw two of them. Same thing for krypton. That's the Lewis structure. You draw two of them. Here's where things get a little bit weird though. They're both just an atom, but if we think back, these are both noble gases. They're right here, argon, krypton. Remember the trend for atomic radius? As we go down a family, the atoms get bigger. So when we draw the circles here, I'm going to draw it to scale that argon is smaller than krypton. That's going to be important here. So argon's a smaller atom. Krypton is bigger. And then there's some intermolecular force here, which we will find out soon. Okay, so we need to find out what the intermolecular force is between the argon atoms. Question, is the molecule polar or nonpolar? Well, is this balanced and symmetrical? Yeah, it's just one thing. Okay, so it is definitely balanced and symmetrical because it's just a circle. So this is going to be nonpolar, which means our only option are dispersion forces, which are the weakest. So that's dispersion. Same thing with krypton. It is nonpolar because it's all by itself. It's just an atom of krypton. So it also has dispersion forces. So now the question is, if they're both dispersion, how can you tell which one has a stronger intermolecular force? If you look back in your notes, it has to do with size, which is why I paid attention to the size of argon and krypton. Krypton is larger, it has more electrons, and so dispersion forces are going to be stronger because you'll be able to get more electrons kind of crowding in on one side at any given moment, just by chance, because there's a bigger area, there are more electrons moving around, and so nonpolar molecules or atoms here that are larger will have a stronger dispersion force than the smaller ones. Okay, so check your notes for that one, but for the answer, it is krypton because it has more electrons. It's a larger nonpolar molecule. Okay, so the dispersion force will be stronger. That's always going to be the case if you're comparing two things that have dispersion forces. All right, and then the last one that I'll do here, CH4. Easy Lewis structure here. And then CH3Cl. One of these is now a chlorine. Okay, so we have our Lewis structures. We need to figure out the intermolecular force. We'll start with this one. First question, is it polar or nonpolar? Is it balanced and symmetrical? Here's what it looks like. It is definitely balanced and symmetrical. So this is a nonpolar molecule, which means it has dispersion forces. Remember, those are the weakest. This one, on the other hand, one of those hydrogens now is a chlorine. It's different. So when we ask if this one is polar or nonpolar, hopefully you notice that this one is now polar because it is not balanced and symmetrical anymore because that side is different with the chlorine. Okay, so since it is polar, we have to ask, is H on the phone? Do we have any FH, OH, or NH bonds? We have a lot of H's, but none of them are on the phone. They're all bonded to carbon. So that says dipole-dipole then, if H is not on the phone. Okay, so dispersion versus dipole-dipole. Dipole-dipole is the stronger force, which means this molecule would have the higher boiling point. And remember, what we are doing when we are boiling is we are breaking the intermolecular force that is between these molecules. So when we boil something, we're breaking this attraction. We are not breaking the covalent bonds here. Those are too strong, they stay together. But when you have a liquid, these things are interacting and rolling around. If we boil it, get it hot enough, then they get enough energy to break free from those intermolecular forces. Okay, so it's harder for these ones to break free than it is for these ones, because there's a very weak attraction between these methane molecules. So they're already actually in a gas at room temperature, methane gas. Okay, so that is a little bit of your intermolecular forces homework assignment. Hopefully that helps you out. Pay attention, you need to follow those steps. You need to have 2 Lewis structures for each of these with the intermolecular force labeled. Your flowchart will be very helpful for you to do that. Okay, good luck.